So today we move into chapter 4 on two-dimensional steady-state conduction. So we've covered the steady-state conduction, but have we covered two-dimensional yet? No, we haven't. It was only one-dimensional. We haven't gotten to transient. We're still steady-state. It's next chapter, I believe, is transient. So anyway, I tried to highlight what's up with this chapter. Alternative approaches, I'm going to skip that. Take a look at it, but how about method of separation of variables? Highly mathematical. That's really why EA2 is a prerequisite to this course, in addition to EA1. PDEs, partial differential equation, solving for temperature both as a function of location x as well as location y, steady state. A very challenging problem. Okay, then the next we could go to a very simple conduction shape factor. You know, a lot of people have worked in heat transfer before us, and they've tabulated a lot of solutions to common geometries, common problems. And so there'll be this nice conduction shape factor, and we can use it, just say Q is equal to Ka over L delta T. That's our approximation we used many times for Fourier's law. And what they said was this area to length ratio, that's simply a geometrical relationship between some isothermal surface T1 and some isothermal surface T2. Hence, they just replace that with S, and so Q is equal to K shape factor delta T, a geometrical shape factor. Now, it depends on where your two isothermal surfaces are, T1 and T2, but primarily it's a function of geometry. Okay, then we're going to talk about finite difference equation. So what we do in this class is we take a very physical interpretation of our difference equations. We really do energy balances for nodes in a mesh, and we identify little volumes for each of those nodes. And so in heat transfer, we put more of a physical interpretation on our difference equations. We move away from just simply a mathematical, I don't know anything about what this differential equation represents. No. We go to an energy balance approach to the difference equations. And that's pretty much the chapter. Let's jump into it. In 2D, so a coordinate system X goes from 0 to L, and in the Y goes from 0 to W. That's our box, 2D. And somehow we're looking to solve for the temperature at every location in that box. The simplest type of boundary condition is that this temperature on this face is given. The temperature on this edge is given. Maybe T1 and T1 are both the same temperature, as well as this edge are given. It's all three edges have the same temperature, T1. What about the top edge? It's the only edge that has a different temperature, and it's all constant temperature. Professor, what's happening at this corner where it's T1 coming from below and it's T2 coming over? Mathematical singularity. Welcome to the mathematics, right? It's inconsistent. You can't have T1 different than T2, and along the right edge and the top edge, they're going to come to a corner. That's a problem, mathematical problem. Okay, same what over here, but don't think too much about that. Basically, you can solve this problem. You're going to get a series solution. You're going to get an infinite number of terms that you sum up. Well, how do you solve it? First of all, our governing differential equation would be something like the second derivative of temperature with respect to x squared plus the second derivative of temperature with respect to y squared. Do we have any Q dot? Nope. Do we have any transient? Nope. No heat generation, no transient, just conduction. Constant K. K is constant through the material. K is equal to just a constant. Okay. Well, introduce theta. What's theta? Some dimensionless temperature difference. So it'd be like T minus T1 divided by T2 minus T1. All right, let's check it out. Along this bottom edge, right down here, they say theta is equal to 0. All right, if along this bottom edge, if I put in that the temperature is always T1, well then I put in right here T1, then I have T1 minus T1, then the numerator, it's always 0. All right, they say along the top edge, theta is equal to 1. Okay, well, instead of putting T1 in along the top edge, you put in T2. So numerator is T2 minus T1. You divide it by T2 minus T1. Yeah, it's theta is equal to 1. So they make it more abstract, don't they? So here is our new differential equation. Where'd temperature go? Sorry. We want to make it more abstract, more, this is just the approach. Okay, so theta. You're solving in terms of this definition of theta right there. What about the boundary condition? Let's do the boundary condition over here. Well, I already did it, or it's done in the illustration. It's equal to 0. So theta at x equal to 0 for all y, it's equal to 0. Isn't that the way you describe this boundary condition? And then how about this one? You say theta for any x. X goes between 0 and, maybe I should emphasize that up here. Put y goes between 0 and cap w. They never write it like that. They write it the way I showed you. Likewise here, x goes from 0 to L for any, for y equal to 0, that's equal to 0. That's that boundary condition. And on this side, they'll put theta at x equal to L for any y between 0 and w, that's equal to 0. And then in the top, I didn't leave enough room, so I'll write it up here, that theta at any x for y equal to cap w is equal to 1. Now you have 4 boundary conditions, 2 for the x, 2 for the y. You have a second order, PDE. Go for it. You're just chomping at the bit. Well, we don't have time to repeat what you were exposed to and mastered in EA2, but you come up with the series solution. Look familiar? Sure. And let's just stare at it for a minute. What is this? Sine of some terms, group of terms. And this n sums from 1 to infinity. So you have n 1, 2, 3, 4, 5, etc. And then what do we have here? Cinches. Hey, our old friend the cinch. So you saw it before, EA2. You saw it again in last lecture. So here it is that n, so we have a series summation. So it's sinusoidal in the x, and it has a cinch form in the y. And you have these terms that go back and forth between negative and positive, because -1 to an odd exponent gives us a negative, and -1 raised to an even gives us positive. So it's changing signs. Anyway, nasty solution, isn't it? Before computers, this is what would happen, and people actually did this by hand. Not that often because it's very expensive. Computers made it a lot cheaper. Slide rules made it a lot cheaper too. All right, so you can get an analytic solution. Now there's many approximations out there before the computers came along, and so I've already covered what that shape factor is. The shape factor is simply an area to length ratio. It's geometrical. Take a look at the implied SI units for the area to length ratio. Clicker question. Answer A, B, C, or D. Is the dimensions, the SI units, dimensionless for the shape factor? Is it meters? Is it inverse meters? Or is it meters squared? So what is it? Is it dimensionless? Is it meter, inverse meter, or meter squared for the SI unit for the shape factor? So somehow one person is somewhere else today. But meters squared for the area, and then meter for the length, and then it turns out to be just meter. for the SI units, right? Right. If I had some crazy configuration, we're going to look at a lot of them. Here they are. They're tabulated in this one, table 4.1 of our textbook. They have maybe, what is this, isothermal sphere. So the sphere is buried in a semi-infinite material. So this is the semi-infinite material like that. And the material has a thermal conductivity of it. The sphere has diameter d. The entire surface of the sphere, you can think of it as being hot with temperature T1. You have to have isothermal surfaces for this to work. It's all T1. And then T2, the semi-infinite surface above, the depth of burial is Z. Z doesn't go to the top of the sphere. What does it go to? The center of the sphere. All right. Well, as long as Z is greater than d over 2, what happens if Z is less than d over 2? It's not quite buried, is it? It's got something poking up out of the surface. You can't have that. Then you get this equation. Where'd that equation come from? A lot of old textbooks. And somebody worked on this a long time ago, maybe 100 plus years ago. And they tabulated these things for us. And so it's really simple to use the conduction shape factor. So Q is equal to K. I like to put S after the K, but that's okay. They put S in front of the K. And then the delta T, hot minus the cold. And you kind of figure out what is the direction of the flow from the hot buried isothermal sphere to the cool surface of the land above it. Sure, that would be it. Some of these are very hard to interpret, like how did they ever come up with that? But you know, a lot of textbooks will have references and then you can go back and look at them. Some of them are not in the English language. I've tried to look at a few of them in the derivation. You got to be, in different language, German mostly. Okay, here's another one, horizontal isothermal cylinder of length L. Buried in a semi. So all you have to do is read, find your right case, and then apply it. That's all you have to do. Two parallel pipes are buried, spaced 0.5 meters apart, in soil having a thermal conductivity of the soil. The pipes have outer diameters, so one is a little bit larger than the other, 80 millimeter diameter versus 60 millimeter diameter. The surfaces are 175 and 5, so one's hot, one's cold. You're going to have the heat transfer from some pipe to another pipe. This one's diameter D1, this one's diameter D2, and they have some separation distance, maybe Z, separation distance. And as you interpret that, would that be the edge of the pipe to the edge of the pipe or the center of the pipe to the center of the pipe? Center to center. Yeah, center to center. And they have these isothermal, so you know one is hot. And it looks like the larger one is the higher temperature and the cooler one. Make sure when you use the conduction shape factors, you have two isothermal surfaces. In this 2D, they are lines like that, the surfaces of the pipe. What is the heat transfer rate per unit length between the two pipelines? Well, you would look for Q is equal to K of the material that it's conducting through, which is the soil. Then you have the S, then you have the delta T. Well, if I want Q divided by L, isn't that Q prime? Then I would have to divide this by L. And often what you'll find is that shape factor has some length in it. And so it naturally will collapse out. We go to the table. We look for the case that makes sense. So case 4, conduction 2 cylinders of length L in infinite material. So the L is in the third dimension, you can't see it. Diameter 1, diameter 2, that's our spacing, not Z but W. And they have some criteria. Check that the length is greater than D1, much, much greater. Well, yeah, very long pipes. Okay. And then also the length needs to be much, much greater than the separation. So we need to be talking about more than 5 meter length of the pipe. for this to apply. But here's the equation for the conduction shape factor. Oh my, what is this COSH to the -1 of something? Let's have a clicker question, huh? You have your calculator. Let's do on your clicker, let's do what is the cosh to the -1 of 2.8, and we'll input it, when you calculate it, we'll input it numerical into our clicker response. Cosh to the -1 of 2.8. Yeah, let's take a look at our results. Okay, so 1.69. Well, first of all, there's that length, so that you can see that at the S divided by L, that's going to cancel that L right there. So you just 2 pi over this cosh -1, arc cosh of blah, 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 and then you plug it in, and you will calculate 100.2 watts per meter, putting your temperature difference in the thermal conductivity. Plug and chug. Students love shape factors, right? Okay, you can also use it in the resistance concept. So we have some Q is equal to K, shape factor, delta T. Well, then the resistance would be, instead of L divided by Ka, it would be 1 over Ks. It's just the resistance using a shape factor. All right, let's solve another problem where we'll use that. So we have a hole of diameter D, 0.25 meter, drilled through the center of a solid block of square cross-section with W equal to 1 meter on each side. The hole is drilled along a length or depth. I'm going to call it L. I don't like a lowercase l. I wish that was a cap L. I should have changed that, huh? Of the block, which has a thermal conductivity K of 150 watts per meter Kelvin. The 4 outer surfaces are exposed to ambient air. Oh boy. So out here we have the H2 and the T2 infinity. I'm going to repeat that. T2 infinity. The T2 infinity is 25 degrees C, and the H2 is 4 watts per meter squared Kelvin. Not very, it's ambient air. It's not blowing. That's pretty low H. All right, how about inside? Hot oil is flowing through the hole. Its T1 infinity is a whopping 340, so right up here, 340 degrees C, as well as an H of 50 watts per meter squared Kelvin. All right, what is the rate of heat transfer from the hot oil to the cold air? Well, you've got to first get it out of the oil and to the inner surface hole of the block, of the solid. That's a resistance, that's a convective resistance, a 1 over HA. Resistance, a convection, I would call it 1 and area 1. And then we're going to have some resistance of conduction through that block. Well, that's an L over Ka, but we don't have a L or an A. We have a shape factor, or we can get a shape factor, 1 over Ks. And then we have it 1 over H on the outside, that's 2, and area on the outside, A2. Let's go ahead and identify each of these nodal temperatures. This is T infinity 1, which is 340 degrees C. This is the temperature, I'm going to call it surface 1, or or just even T1, you can call it T1. And this is T surface 2, and then this is T infinity 2, which was 25 degrees C. We don't know the temperature right here. We don't know the temperature right there. Actually, the inner hole temperature is part B. That's going to be our TS1. and our outer surface temperature of the block is TS2. So those are going to be solved for part B and part C. Okay, that makes sense? So what we'll do is we'll put in our H values. So we have 1 over our H1, which was 50. You would put your units in there of watts per meter squared Kelvin. Okay, and then what do we have for the area 1? Pi D1, which is 0.25 meters, pi D1 width and length. Now, what is my length? 2 meters. Pi DL, isn't it? Isn't that my area? Yeah. Okay. So then the second resistor, these are in series, so I'm going to add them up to get the total resistance. R total, okay, is my 1 over thermal conductivity, 150 watts per meter Kelvin. And then I have my shape factor. Okay, I have to go and find that in our table. Here's our table. Get this out of the way. And so our shape factor is 2 pi L divided by the natural log of 1.08 W over D. All right. If I, let's just put it in the equation. 2 pi L, 2 meters, times the natural log of 1.08 W, which is 1 meter, divided by D, 0.25. You can make an intermediate calculation of that shape factor. Okay, we'll then continue on out here. Is 1 over H2, which is 4 watts per meter squared Kelvin, and the area. What is my area 2? 4 meters times 2 meters. 8 meters squared, right? Does that look okay? Do they all have the same units? Okay. Let me do this. I want, well, I can just continue on if you want. I have to look at my notes for actual numbers. The formula is 2 pi L divided by the natural log of 1.08 W over D. I'm sorry? Oh, this is 1 edge, 2 edge, 3 edge, 4 edge, and each of them are 1 meter long, 4 meter. That's where the 4 meters came from. Is that what you're asking? And then depth of 2 meters. That's right. I should have switched it to cap L. Okay. Okay, well, when you make this calculation, this becomes 0.012732 Kelvin per watt. This becomes 0.000776 Kelvin per watt. And this becomes 0.031250 Kelvin per watt. When you add them up, you get a value. But if you take a look, which one dominates the resistance? The largest resistor is right here, the convection on the outside. It has a low H and a large area, but it's the low H that does it in. You can go back and quantify what percent of the resistance is due to the convection on the outside versus the conduction through the solid versus convection on the inside. All right, so we get R total, and then we get Q is equal to the delta T divided by R total. And you'll calculate 7,038 watts, or 7.038 kilowatts. All right, once I know this Q, how do I calculate the temperature TS1? Let me do this. Let me pause, and I'll walk around. I want you to show me We just calculated what this Q is. This Q is 7038 watts. How would you calculate TS1? And I'm going to give you a big hint. This resistor right there, that's the value of the resistance. So I want a couple people to show me they know how to do that. Temperature surface 1 is the temperature infinity 1 minus the Q times the R. I'm going to call this 1, R1. Did I do that right? And so there you go. So hopefully you were able to calculate 250.4. Anybody not be able to do that? Okay, let's march on. Same thing over here. You have the flow. It's still 7,038 watts flowing through this resistor. You know this temperature. You back it up. Professor, what happens? We already calculated this one. Why don't we just keep... You're going to get the same value. Go both the ways. You'll get the same value. Okay. All right. Now we took into numerical methods. So the finite difference equation, in response to having taught this before and students looking at me and telling me, no, we never learned that, never, believe me, never taught it, never saw it. How many people have seen this book? Chopra and Canali. Yeah. This chapter, numerical differentiation, any equation like the first derivative, like f prime is equal to f at x at, what is this, subscript I plus 1 minus f of x of I divided by the spacing h, which is the difference between x at the I plus 1 minus x at I. Okay, or how about this one? This is, nobody really uses these higher order. This is, if I look at the error term on this, this is like order h squared. Nobody does that. How about the second derivative? This is the one everybody remember. So if you had a node, you have a node, you have a node, you have the x at I minus 1, x at I plus 1. Then you take the value, well, even this one is even forward differenced on the second derivative, but it's more common to have the f at, a lot of times I'll just call that I minus 1 minus 2 f at I plus f at I plus 1, all divided by the delta x squared, or the h squared. Remember that? You're discretizing it. Okay, you can come in and have a 2D mesh. Remember, we're only doing 2D in this chapter, not even 3D. And you have all of these locations for the x. You have all of these cuts. And so the goal is to solve at the intersections of those grid lines, at the nodes, the distinct temperatures at that location. So I'm looking for the temperature at the MN node. Here's the MN node. Okay, so you would come in with your second order differential equation, second derivative of temperature with respect to x squared. You would replace that by something over here, there, and then also you would have it the second derivative of temperature with respect to y, there. You'd have a little, even put stencils out, old school, real old school. How that node in the middle was determined by the surrounding values of the temperatures at those other nodes. All right. This is all very mathematical, and so that's not the preferred approach by an engineer who's learning numerical methods. Now, once you get more sophisticated and then you go deep into the bowels of some code like the finite element code, then it gets very mathematical again. But then the programmer coded it up. But let's jump over here. Here is the difference of the second derivative with respect to x, the difference second derivative with respect to y. You plug it into here, you plug it into there. Those are all central finite difference formula. You come out with the final bottom line that, hey, the one in the middle is really just an average of the four surrounding ones. That's really what this equation boils down to. But an energy balance or mathematical, this is equal to 0, you have it equal to 0. All right, how do we do this with an energy balance though? Well, this is what you do. You have your surrounding nodes, whatever you want to call them. If you want to number them individually, let's call this node 51 and this node 43 and this node whatever. You can do that, or you can stay with the sort of two index numbering system. Here they have the M, N numbering system for the nodes. So you would have a temperature at that node right here, as well as the M, N plus 1, N minus 1, N node. Okay. And you would be interested in, what do they show by these little arrows? Flow of heat. Rate of heat transfer. Heat transfer. What is the direction compared to this dashed line? What's that dashed line surrounding the node in the middle? What would you think you would call that from thermodynamics? A control volume. And you're going to do an energy balance for a control volume. This is a lot easier, I think. This is the engineer's approach, energy balance. And so what you'd do is you'd say, well, I'd have the Q from the top, plus the Q from the bottom, plus the Q from the right, plus the Q from the left. Now, if I have some heat generation, Q dot, I can have even some Q source, because all of these, the way they're shown, which is the direction of the arrow? It's bookkeeping, and it simplifies it and helps you avoid plus minus errors if you just say everything's into the node of interest, into the control volume of interest. Hence, the source would be a plus in front of it. Now, if it's steady state 2D, boom, that's it. Okay, how would you approximate Q from the top? Well, you'd say, I like the equation K A over L. Then I have the temperature at the top here, it's the M N plus 1 minus the temperature M N. Professor, as I'm solving problems, maybe I'm going to figure out that this is the cold temperature and this is the hot temperature, and it's really not flowing from that direction. It's actually flowing in the opposite direction. Go back to statics. When you put your free body diagram and then you put a choice for the direction of the force, do you remember going in circles and chasing yourself if you ever, in halfway through the problem, decided to change the direction on the free body diagram and go back and modify because you just figured out it's not pushing this way, it's pushing that way? Don't do it. Trust the math. You'll get a negative answer. Your math will work itself out. So this is just a big hint. Leave all the flows in, even if you know that this up here is cold compared to hot. Don't try and change it. So, as I've written it, isn't this assumed to be hot, cold? This will be a positive flow from the top into the control volume. And then you just continue on. For the second one from the bottom, it'd be K A over L. Then you'd have the temperature outside, N minus 1, minus the temperature Mn. Yes, sir.
What's L?
In this problem, that's a great question. I need to get to this. So for this problem, I have area and length to struggle with. What is my area? That's probably the easier before the harder the L. If I'm looking at going from top to the center, inside, what is the area for the heat flow? It's my perpendicular area, isn't it? Would it be the product of this distance right here times the depth in the third dimension? So the area would be the distance delta x times a depth in the third dimension. I'm going to call delta z. But you know what, delta z, you can pick it to be 1, or in the equations, all the delta z's will cancel. Now the harder one. You got the area down. Now, what is the length? Well, is it the length from just a little bit above the line to a little bit below the line? you know, epsilon above to epsilon below, 2 epsilon, is that my length? Or is the length from the middle to the middle? Which one is it, 2 epsilon or middle to middle? Middle to middle. It's middle to middle. Now, this one, they show delta y going from edge to edge. If you have a grid where the sizes are changing, delta y's get larger and larger as you march, it's a little more complicated. But believe me, everything that you're exposed to for this lecture, for our homework, for exams, delta y doesn't change. This is also delta y. This is also delta y. They're the same. They're not, it's not expanding, okay? So guess what the distance is between the node and the node? That distance. Delta y. So the length is delta y. Now there's a few steps of logic in there. Hopefully you followed them. Hopefully you thought, this is pretty trivial. Good, I'm glad. But believe me, I've taught it enough times to know some students stumble. But they need to calculate that. So now, when you come in here, you would replace, oh, this area would be the delta on the x divided by, and delta z is going to cancel. You can put it in there, divided by delta y. Now, almost always, not always, but almost always, what do you think the relationship is between delta x and delta y? Graphically, for this problem, they look pretty close. Delta, almost always, delta x is equal to delta y, but not always. You have to be careful. Sometimes you have a long versus, short control volume. So you're going to replace all these areas to lengths by ratios of x's and y's, or delta x's and delta y's, or delta y's over delta x, because look at, when you're now, for the one coming from the top and the bottom, the areas are delta x's. And the lengths are in delta y. But how about for this one? The area coming from the left, the area is delta y, the height. And the length is delta x. All right. Oh, what is q dot source? This q source will be my q dot times delta x times delta y times delta z. Remember, this is so many watts per meter cubed. Then I have meter, meter, meter. They cancel. I get just watts. All these terms are watts in, watts in, watts in, watts in, watts in. Professor, if this one's maybe 5 plus 5 watts in, and we know they have to sum to 0, some of these terms, aren't they going to have to be negative? You're absolutely right. The math will take care of itself. So if this is 5 in, and this is 5 in, and this is 1 in, and this is 0 in, guess what this has to be? Negative 11 watts out for the energy balance to work. So what you do is you get a equation, I call it energy balance for the node, let's say node 1. Then you get an equation for energy balance node 2, then energy balance node 3. You know what? If you have 10 unknown temperatures, you need 10 energy balance equations. Then, glad you took a numerical methods class, you'll have 10 equations and 10 unknowns. Luckily, they're all linear, algebraic. You could set them up in a matrix. You can do the AX equal B. Big A times X is equal to B. You can solve for X, column vector of unknowns, A inverse B, linear algebra. Covered in EA1 as well as numerical methods. So we don't have to recover it. Let's solve this problem. Unfortunately, these problems get a little longer. We have a long rectangular rod. Hey, I don't see a rod, I just see this two. Okay, you got to project it in the third dimension to get the rod. Okay. It's a uniform volumetric heat generation rate of Q dot equal to 4 times 10 to the 7 watts per meter cubed. Okay. And a thermal conductivity of 21 watts per meter Kelvin. 2 of the sides are maintained at a constant temperature of 285.6 Kelvin. How did they come up with this? I don't know. So these have uniform temperature. You can see they discretized it. Can you see where they have this node right here, and that call that 1, node 2 right there? node what? A. And they're going to talk about the temperature at node A. This is the temperature at node C. This is node 3. This is node B, temperature at B. So they put a node right here. I don't know why they didn't put a node here, 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 and here. If I was an illustrator of the textbook, I would have put nodes there. I would have put round black dots to be clear. And then I would have said, you know, I know the temperature at this point. The temperature at that point, 285.6, 285.6, 285.6, 285.6, 285.6, 285 point, a little boring, wasn't it? But that helps. I know that they're isothermal edges. Now, this illustration says the others are what? See that? Can you see what they're illustrating? They're insulated. It's insulated. They somehow tell you the temperatures at A, B, and C are known. The temperature at A, where is node A? Right here. We just put in 360.3 Kelvin. Temperature at B, put in 342.4 Kelvin. Temperature at C, 322.5 Kelvin. Now knowing all of those temperatures, all you have to do is solve for 3 unknowns. Get the temperature at 1, 2, and 3. That's it. I just want to solve for temperature at 1, temperature at node 2, temperature at node 3. So first thing, discretize. Get the volume for each node. Even if the node already knows the temperature, just get the volume. So what you do is you cut in between. You cut in between. You cut in between on a horizontal as well as a vertical. You cut in between, and you cut in between. All right. So if I was interested in this corner node right here, isn't this the volume or the area that's associated with that node? All right. How about this node right here? What is the volume or area associated with that node? Isn't that true? Okay. How about this one TC right there? Let's color it green. Isn't it this? Right away, you have different size volumes if it's in a corner, an edge, or an interior node. All right. Let's now focus on node 1 right here. And here is the volume associated with node 1. All right. I want to get an energy balance for node 1. Go slow. What I would do is I would say, I'm going to have assumed flow in. All right, just like that. There's in from that node. You'll have in across that edge, and you'll have in across that edge, plus you'll have your source. So I like to draw it maybe going slow here. I'll have something which is coming from my surface. I'm going to call it T surface, TS, minus T1. I'm going to have something coming from this node right here. What node was that? C, minus T1. I'm going to have something from this node 2 coming in. Those are the temperatures that drive it coming in. And notice I always put the exterior minus the interior. It's always minus the node of focus, T1. Now, they're going to have the thermal conductivity, thermal conductivity, thermal conductivity. Now the hard work. My area to length for each of those. So, the easiest probably is this area right here. That's from the 1 TC below. What is that area? It'll be that discretization delta on the X, which is 5 millimeter. Before I substitute numeric value, just leave it as a delta X. So won't it be delta X times a delta Z? Forget the delta Z. You know, the delta Z's are going to cancel, okay? So now, what is my length going from TC to T1? Delta Y. I pause. Did we do this one okay? All right. What about this one over here from the T surface going that way in? What is my area? Half of delta Y. Delta Y over 2. What's my length? Delta X. All right, come over here now to this one, coming from node 2 in. What is my area? Delta Y over 2. What is my length? Delta X. The other term that I need to put in is my Q dot, my source term, and I multiply by how much area is associated with that real estate is. What do I multiply? Isn't it delta X, delta Y over 2, and then I put the delta Z, but they're all going to cancel, so there, I just call it quits. Does that make sense? Or if you want, you could put a delta Z of 1 meter, everything 1 meter depth. That'd work too. But the delta Z's cancel. All right, this is my Q dot. I pause. Does it look okay or do I have an error? Who agrees? Give me a thumbs up. It's only this much real estate. That's a delta Y over 2. This is a whole delta Y. Yeah. You have one equation, but how many unknowns do you have? You have an unknown T1 and you have an unknown T2. Can you, as a bright engineering student, solve for 2 unknowns with 1 equation? No way. Guess what you need? And where are you going to get it? Energy balance for node 2. All right, where's node 2? Right there. So let's go a little faster. K, I'll have delta Y over 2 divided by delta X. This is going to be the flow from 1 into 2. Professor, this is so confusing. Over here we had T2 minus T1 in energy balance for node 1, but now you swap them and you have T1 minus T2 for the energy balance in node 2. All the flows flow into the node of interest that you're doing the energy balance on. It's good bookkeeping, good strategy. All right. And then we're going to have flow from 3 into 2. That'll be a K. And then the area is a delta X and the delta Y. All right. And then we're going to have the flow from A into 2. And that'll be a K. It'll be a delta Y over 2 delta X. And then I have my source term, Q dot, times the volume associated with node 2, which is delta X times delta Y over 2. That has to sum to 0. That's great. I got now 2 equations, but guess what? T3 is also an unknown. So I've got T1, T2, T3s. Can I solve for 3 unknowns having 2 equations? No. You need a third equation. Guess where you go to get the third equation? Energy balance for node 3. Finally, we'll get 3 equations, 3 unknowns. Now you can solve for them. Okay, now this will be a K. Oh, let me just kind of draw it like this, my temperatures. For node 3 right here, I can come from 2 to 3. I can come from B to 3. That's a B. I could come from side into 3, or the surface or edge or whatever you want to call it. And I can come from C into 3. So I'm going to have 4 conductions plus my source term, which I didn't leave enough room for, Q dot times delta X delta Y, and all of that is equal to 0. Hopefully you follow that. Sorry, I'm running out of real estate. All right, so we're going to have 4 conductions. north, south, east, west. Okay. T2 to T3 is going to be, the area is going to be a delta x. The length is a delta y. From B, which is right here, into 3, the area is a delta y, the length a delta x. And then from surface down below into 3, the area is a delta x and the length is a delta y. And k times c into 3, the area is a delta y divided by delta x length. Now, if delta y is equal to delta x, which is true for this problem, they're the same. Then if you even mess up delta x over delta y in the equation, it really doesn't matter because they're going to cancel. See that this is just 1, 1, 1, 1. But if delta x was different than delta y, then you'd have to double check to make sure. All right? Hopefully that makes sense. Did it look okay? Now the volume is a full, for node 3, a full delta x times delta y. Not a delta x times delta y over 2. Okay. 3 equations, 3 unknowns. You have to solve them. It would take me a little too much time, but you would manipulate these. They're just linear algebraic equations. You need to be able to, prerequisite for this course, solve 3 equations, 3 unknowns. They're all linear algebraic. There's nothing special about them. It's work. I didn't say it wasn't. But these are the 3 temperatures that you get. Yes, sir? That this is the area, and then we all have a unit delta z of 1 meter. Pick it that way. Yeah. Make good sense? Okay. Now, D and E are harder. Let's talk about it for a minute. The heat transfer rate per unit length from the rod using the nodal temperatures. Well, I think part E is easier. Let's read that. The heat transfer rate per length from the rod using, everything's the same, D and E, but volumetric generation rate and the rod dimensions. Basically, everywhere in the rod, there is heat generation. So if I wanted to know what's getting to the surface out here that's uniform temperature, it's everything in the interior that's being generated. Q dot, this source right up here, times the area per 1 meter depth, and then I'm going to say, oh, I picked 1 meter depth, hence it's 6,000 watts per meter. This is Q dot times this entire length in the X, and then this entire length in the Y. So how long is the width here in the X? How many millimeters? 15, exactly. 15 millimeters. How high is the height, the total height in millimeters? 10 millimeters, right? 2 5s. And so this will be 0.010 meter times 0.015, sorry, 015. Computers catching up, meters. And then I know I'm putting it per length, so however you want to handle that, but this gives you the answer of 6,000 watts per meter length. Part E is solved first. Now the last part, part D, which they get the same answer. Let me go over here, clean this up. What gets to this node, this node, this node, this node, this node, and this node? Just sum them all up. Well, what gets to this node is what is conducted from that node. Okay. What gets to this node is what's conducted from that node. what gets to this node? Well, really you don't have any conduction other than from the sides, so but that's already the surfaces. I don't worry about this one to that one. They're the same temperature. So it's just coming from the interior. So then this is a flow, and then this is a flow, and then this is a flow. Remember, this is half an area. So I would calculate from 1 to the surface, from TC, this one plus that one, 2 pathways from TC, from node 3 to the surface, and B to the surface. Notice that from B I have a half area, from 1 I have a half area, but from C I have a full area and a full area and a full area, like that. So watch out for your areas. That won't get you the total. What you have to also do is you have to add up the volumetric source. This part gets to that node. This part gets to that node. This part gets to that node. This part gets to that node from the heat source. Gets to that node, and that part gets to that node. And when you do that, you sum up the generation associated with each of those nodes, because that's what's getting to that node, plus the conduction from the interior to each of those nodes, you'll actually get the same value, 6,000 watts per meter. Now, if you keep all your digits on temperatures, it'll even be better. But if you start truncating your temperatures and you just said, oh, this is 333, or this is 323, well, you're going to have some little difference in the 3rd and 4th decimal place on that Q prime. But run here, you get 6,000 watts per meter. All right, ready to move on? All right, we have another one of these problems. A flue passing hot exhaust gases has a cross-sectional area, a square cross-sectional area, 300 millimeters to a side. So here is the interior, here is the exterior. Its interior, where the flue gas is 300 millimeters. Now, this is the thickness right here of the wall of the flue. So a little bit of geometry. Can you tell me what is the dimension from outside to outside? We'll take a numeric response. So there's 300 millimeter on the inside, and the brick is 150 millimeter thick. And all I want in millimeters, in units of millimeter, what is this distance right here? Good, 600, right? 600 millimeter. That just help you wake up. All right, they're given a thermal conductivity of the brick, the interior and exterior surfaces. So everywhere on the gas interior is a temperature of 350 degrees C, and way out here it's 25 degrees C. A huge temperature gradient across the brick from inside to outside. So the interior temperatures, those nodes right there, all 350 Kelvin. I don't know why they didn't put T out and then, oh, the T out's 25 degrees C. But anyway, they just put 25, 25, 25. Okay. Now, the grid spacing, they'd introduce some nodes for you and 75 millimeters. So because it's 150, it's like 75 and 75 equal 150. And then you have 75 and 75 equal 150. And because this interior is 300, going from here to here, that's 150 just halfway. Then they introduce a symmetry section. Can you see the hatched part is a symmetry section? You can exploit symmetry because if it's symmetrical, I just need to solve for those unique temperatures, and if I expand it by flipping over my symmetry boundaries, I can reconstruct the whole thing. I can get the temperature everywhere, but it's like the temperature in the middle on this edge would be the same as the temperature in the middle on that edge, the same as the temperature in the middle on that edge, same as the temperature in the middle on that edge, because it's symmetrical. Likewise, the temperature in the middle on this edge is the same as the temperature in the middle there, temperature there, there. Okay, how big is that symmetry section compared to the whole cross section of the flue? Is it like, do I take this symmetry section and 4 times it and I get the whole reconstruction, or what's my factor? How many? What? It's 8. It's 8. All right? It's 8 of them. So you flip it out. There's a 2. Then you can flip it again. 3, 4, 5, 6, 7, 8. Very good. 8 of them. You have to see those symmetry things. Okay. Using a grid spacing of 75 millimeters and assume the temperatures at node 2 and 3 are given, this temperature and that temperature. So here is the temperature. There's node 2 and node 3. They just gave them to you. I remember this one. It was painful. If you go to Wiley Plus, which I deleted this problem, they put in T2 as 108.3. Typo. Can you believe that? It took me a while to figure out, like, why won't this work? And then you back it up, and then you find out, oh, that's the error. Anyway, this number will work, and that number will work. So they give you those 2 temperatures. They want you to calculate T1, T4, and then the heat loss in the flue per unit length, depth of the flue. Notice that you'll have to use that factor of 8 because you'll calculate it for the symmetry section, then say, hey, I have 8 of these symmetry sections to make up the whole flue. All right. So how am I? Look at, they did, it's so easy for you. They even give you the control volumes. Look at the control volume for node 1. Look at the control volume for node 4. All right? Okay, so let's do an energy balance to calculate energy balance for node 1. I would go slow. I would say I'm going to have some flowing in from the 350 into 1. I'm going to have some flowing in from the 25 into 1. Professor, I know the 25 is lower temperature. Assume mathematically it's flowing in. And that's the best way to write the equations, and it'll do you good. And then here, flowing in from 2. So do I have any source, volumetric heat source? No. So let's write our equation. I would put like T, I'm going to put 350 because I know that one. 350 minus T1. I'm going to put in 25 minus T1. And then T2, which is known to be 180. Come on now. 180.3 minus T1. All right. Now I have to put my K's, my plus K, and that's all equal to 0. I have no heat source. I can tell you right away, the K's are going to cancel my energy balance. I just look at it. But you're going to need the K when you calculate this Q prime, part 3, or part C for this problem. Okay, what about my area to length? From 350, what's my area? Delta Y, no, delta X over 2. What's my length? Delta Y. Now, because the delta X is equal to delta Y, you just cancel those 2, and you're left with the half. But don't forget the half. You have a half area. Okay, keep going. How about for this coming from the bottom, 25 in, wouldn't it be delta X over 2 divided by delta Y? Yeah. How about from the side, 180 T2? Wouldn't that be delta Y divided by delta X? But they cancel. The K's cancel. And I'm left with actually one equation with one unknown. Because they separated them, this is kind of neat. You can just solve for that one unknown, and you'll calculate 183.9. All right, you do the energy balance for node 3, and you'll get one equation for one unknown, and you can then solve for T3. No, I'm sorry, T4. We want it for node 4. Solve for T4. One equation, one unknown, you'll solve for T4. All right. Q prime. That's Q per unit length. How many watts per unit length of this flue? Well, to calculate that, I would say Q prime is going to be 8 times Q of this one section per unit length. All right. So 8 times, what is my Q per the one section? Couple ways you can do it. You could say from this interior to 1, this interior to 2, this interior to 3. Sum those 3 up. Sum those 3 flows up. They're all from the hot interior to and in, moving away from and toward the outside. Somebody says, well, why don't I do this? Why don't I sum this one plus that one plus that one plus that one? They'll work. They'll give you the same total flow. Okay? But I'd rather sum 3 terms than 4 terms. And so it'll be the K. Then I'll have an area to length from this surface into 1. That'll be my delta X over 2 divided by delta Y times T. Well, I'm going to put Ti minus T1. Okay. Then I'll have plus K times delta X divided by delta Y times Ti minus T2 plus K times delta X divided by delta Y times Ti minus T3. Close. Professor, how come I have nothing from the inside surface flowing to node 4? Because there's no shared area between that node and node 4. The control volume for node 4 shares an edge with this node and shares an edge with that node, and this is a symmetry edge. There's no flow across it. Does that look okay? Can you do this one? Can you finish it out? Can I stop here? All right. Let's do that. We'll stop. All right. This one's very mathematical. So some materials can be fabricated to have a spatial distribution of properties like the thermal conductivity. So consider this L by L two-dimensional object where this is L is 20 millimeters. And the thermal conductivity K is a function of location X. And it's just given by this equation. They curve fit it to make it look like that. So it's very mathematical. Can you do the math? That's what this problem is all about. Can you do the math? So part A, determine the spatially averaged value of the thermal conductivity. So if I had K as a function of X and I wanted to get an average value, what equation do I use? K average, K bar, K whatever? What symbol notation do you want to use for some averaging? How would you do it? And I have K as a function of X. Let me pause, walk around, and see if you can write down what equation you would use to calculate what they're asking you to calculate, which is the average K. So sometimes when you have a hard problem, it's best to break it down to a simpler problem. Somebody says, I've got this value of K. K is 20. Over here it's 22, and over here it's 24. I have 3 measurements of K. 20, 22, and 24. All of them have units of watts per meter Kelvin. I'm not emphasizing. And now I say, of those 3 measurements of K, can you give me K average? Can you give me K average? I said, here's 3 measurements. Give me the average of those 3 measurements. What would it be? It would be 22. How'd you get 22? You took the 20 plus the 22 plus the 24 and you divided by 3. The number of them. Or you would do this. If I had n of them, I'd add sum over all of the ki's and I'd divide by n. How many did you sum over? Did you have 10 measurements to sum over, 20 measurements to sum over? And then you remember something that they really didn't emphasize in calculus. There's a relationship between this symbol and that symbol. This is discrete, this is continuous. They're both summations. That's all it is. It's now you're ready to do the K average. You're going to say, I'm going to do something like this in the numerator. Oh, instead of sum, I'll do a continuous sum, an integral, the integral. Okay, now if you wanted, you could say, I've got to integrate over the entire area. It's a 2-dimensional problem. That's fine. Let's do an area integral. And so sometimes they'll just do that. And so this would be K as a function of location X and Y. Hey, it's only a function of location X. I know, but it could be more complex. It could be a function of X and Y. And then you've got to divide by N. N, that's how many there are. What's the equivalent when you do a continuous? Divide by A. That's how big it is. All right. Somebody says, let's work this out a little more because I can see that K is only a function of X. Well, if it's only a function of X, then this can just turn into a line integral, dl, and I'll divide by L. No, not dl, dx. dx, and it goes from 0 to L. This, we start the origin at 0, and we go to L. And so you're going to say, you're going to integrate from 0 to 0.020, isn't that our value of L? Of K. K is going to be 20 plus 9010, x to the 3 halves, dx, divided by 0.020. That'll give us the average value. Now, before you jump too much into the math, what is the value of K at 0? Might as well use that equation and check it. What's the 20? Isn't it 20? Okay. What's the value of K at L? Does it go from 20 to 2,000? 20 to 80? What's it go from 20 to what? So just use this equation, put in x equal to 0.020. That's what L is. And then what value do you get for K at x equal to L? Somebody run that for me? $45.5? 45.5. Now you could even do what's K at L over 2. If you did K at L over 2, it'd come in at 29.01. I'll tell you what, sometimes it's good to know what your answer is going to be close to. What do you think your answer is going to be close to just by evaluating it 45, 29, 20, around 30, around 29? And then this is the final answer. I mean, it's 30.19. So this, at this point, we've set up the math. You can do the integration. I don't need to remind you how to do this integration, or do I? You can do it. Okay, it's pretty tiring. I can see that it's a long lecture. Everybody's getting tired. Okay, so that's how you get this answer. Use this value to estimate the heat transfer per unit length. Well, basically, you have to know that the bottom surface 3 is, or the top is insulated, bottom surface 4 is insulated. Everywhere along this side is 100 degrees C. Every along this side is 50 degrees C. So it's pretty easy. You just have that the Q is equal to the K average. Then you have the area, which is your length, times, I'm going to put delta Z, divided by my length, which is also L, times the temperature on one side, 100, minus the temperature on the other side in degrees C. The lengths cancel. I bring this delta Z over, and I get Q prime. And you just use that K average times 50. K average times 50, there you go. 1510 watts per meter. Does that look good? Done? That was pretty simple. Let's jump into another one. Nope, that's the end. So hopefully you know how to solve problems with the energy balance, how to do discretization, conduction shape factors, do some math. You have to be able to handle the math. Okay, at this point, you had a question about a homework problem. All right, so this was one of the homework problems, correct? So what we have is a certain diameter. Here it is for this draw, 0.55 millimeter or 0.55 meter diameter thin-walled steel pipe is used to transport steam at a pressure of 20 bar in a room for which the air temperature is 25 C and the convection heat transfer coefficient on the outside surface of the pipe is 20 watts per meter squared Kelvin. Let me pause right there. Did anything change other than maybe a number or two between your problem and this one that I'm solving?
That's fine.
It's okay? All right. The emissivity of the pipe is 0.8. All right. The steam side convection resistance inside the pipe may be neglected, meaning that the inside wall of the pipe, which is thin-walled, is going to be at the saturation temperature of the steam, which is at 20 bar. You have to look that up. Tsat at 20 bar. All right, what is the heat loss per unit length of the bare pipe with no insulation in watts per meters? I'm going to, on the next slide, that's probably, you did, everybody get that one okay? But okay. Then you add a 50 millimeter thick layer of insulation, and the insulation is given by these, which you look up and find the conductivity, or the conductivity is given to you in the problem statement, I don't recall. So 0.058 watts per meter Kelvin is added. And the emissivity of the outside of the insulation just happens to be 0.8, the same as the bare pipe. Okay, what is the heat loss per unit length? So is this a part that you want to spend more time talking about?
Yeah, because you find that temperature.
Okay, so what you're going to have is a, let me try and draw it like this. I have Q conduction that'll go out to the temperature of the outside surface of the insulation. And from there, it can be transferred in an energy balance for this node. It can be transferred by radiation or convection to the surrounding. So we want an energy balance for a thin surface on the outside of that insulation. Okay, you have flow coming from through the insulation. So that Q conduction would be the K times a delta T, let's say T interior minus the T surface. I'm going to solve for the surface temperature. And you have a resistance, natural log of R outer over R inner, which is the same as D outer over D inner, but working radius or working, doesn't matter, over 2 pi KL. Does that equation make sense? Okay. That has to then all be radiatively and convected off of the surface. So the radiation is the emissivity times the area of the surface, which is pi. What do you want to work in? Radius, 2 pi r. 2 pi r naught, the same r naught that's down here. And then you have the Stefan-Boltzmann constant. Then you have the temperature of the surface to the fourth minus the temperature of the surroundings to the fourth. Now, you have to pause for a minute. Okay, if the air temperature is 25 C, 298 Kelvin is a great approximation for the walls of the room that the air is in. Okay, so that's my T infinity. It's both for the room walls as well as room air. Okay, right away, I'm going to be forced to work in Kelvin in this equation. I can work in Kelvin here and Kelvin there. Because I have Kelvin there, it has to be. It has to be in Kelvin. Okay, so now let's continue on. So when you put in this T1, which is the saturation temperature at 20 bar, Tsat, how many people looked it up? Do you remember what value you have? 486? And is that in Kelvin? Yes. You need that in Kelvin. So if you put in degree C, you're going to be messed. It's not going to work. Okay. Then we're going to add our H times 2 pi. Again, I left out my L. Put the L right there. Just the unit length. Okay, 2 pi R naught L. Okay. Times the temperature surface minus T infinity. Again, I need every term to be in Kelvin. I can't mix degree C and Kelvin in one equation. Okay, now I need to solve for that unknown Ts. And so it's very similar. You need to be able to solve a problem like this on an exam. Okay, with your calculator. So how would you solve it? It's like this. It'd be like A times, I don't know, B minus Ts plus is equal to C times Ts to the fourth minus D. How would you solve this equation, analytic? I'm just throwing out some coefficients, A, B, C, D. Find a root. That's exactly right. So, and sometimes you have to have a good guess on your calculator to start the process. So my guess is it's not as high as 486. I'd guess around 400 because it needs to be higher than the T infinity of the air, 298. So anywhere from, I'd start at 400 for my guess, Ts. All right. So was that the only problem?
I found only one positive root for my equation, and the positive root was less than T infinity, which made no
Doesn't make any sense. So again, here's my write-up for it. Energy balance for the exposed insulation. So I have conduction coming in from the interior. I have convection and radiation going out. That's my radius inside, radius outside of the insulation. Here's my 2 pi KL divided by natural log Tsat minus Ts. That's a conduction. I have the 2 pi RL, then that's going to be my convection. The emissivity, Stefan-Boltzmann constant, Ts minus T infinity. I guess that equation wraps around because I don't see my area in there. I must have left it out. I'm just typing these things up. I need my 2 pi R naught L. Or no, that parenthesis goes all the way over. That's what happened. I tried to simplify the equation a little. Okay, you need numerical root finding. These are the numbers that I had. When I solve it, it comes in at 305.7 Kelvin. So maybe you have a sign switched in the equation. Okay, so once I know that surface temperature, that's the hard part, then I can come back and solve for Q. How do you think I used this one? I just did Q conduction. I just went back to this part of the equation to calculate 391.8. How many people were able to successfully solve for TS? Only a few. How many people that just they could not solve it? Okay.
After I got it wrong, I even worked backwards with the numbers they had, and I got 148, and the correct answer was 128.
So that may be where you had a number that worked. I had a number that worked. But you had a number that somehow for in the Wiley
Yeah, like,
Plus.
I used their correct answers, tried to work backwards, and I got 148, and that was still
I can try to give everybody credit for that problem, but I don't. I tell you what, visit me a little bit after class, and I will verify that Wiley Plus messed up. And then this is also payback, so make sure that you can work that part of the problem too, right? So you find out, oh, it costs this much to install it, and yet I'm going to have this rate of energy savings. Then how many months or years will it take for me to recoup my investment due to the savings on the energy that would have been lost, because of excessive cooling of my pipe. All right, thank you very much for your attention.